Hi, everyone, and welcome back to Intro to Astronomy. We are going to be talking about the solar system where we live. And the reason I have "our" in quotation marks here is because we don't own it, right? It's not something that us on Earth own, but we do live in it. So this is going to talk about a bit of an overview of the solar system. Okay, so this is just to give us an idea of where everything is in our planetary system. So, of course, we have the sun, and then these are going to be the order of our planets. So, we have Mercury, Venus, Earth, which is where we live, Mars, which we have rovers on, we have the asteroid belt, Jupiter, Saturn, Uranus, and Neptune. And then out here we have Pluto, and there is another, if you want to call it dwarf planet, that's near it. And then we have the Kuiper Belt objects as well. There's a few other things labeled on here. I'm not going to get in super detail right now, but I just wanted to kind of give you guys a brief overview of our planetary system. And these first four, whoops, here are what we call terrestrial planets. They have a more rocky surface, terrestrial planets, a rocky surface, and may have atmosphere, may not have an atmosphere, and we'll get talking a bit more in depth about that in the next slide. And then we have our giant planets. So it's going to be these next four. These are our giant planets. And we have included in that gas giants, that would be Jupiter and Saturn, and we have some interesting characteristics. So this is kind of our overall view of the solar system. So let's look at first the content of our solar system by mass. So this is a visual representation, you can say. So say that this, I'm not sure exactly what this cutout is, but we can say that it's probably like the size of a paper plate, maybe. That's what I'm estimating it to be. And then we have little pieces of Play-Doh. So Mercury looks like a tiny little dot. Then we have Venus, it's a bit bigger. Earth, about the same size as Venus. Mars, a little smaller. Then Jupiter is the largest by mass. Then there's Saturn, Uranus, and Neptune. And you can see this in this chart as well, this table. This is in our textbook in chapter 7. And this gives you a percentage of the total mass of the solar system. So the sun, you can see, makes up most of the mass in our solar system, which makes sense. It is the largest object. It has the most mass. The next largest is going to be Jupiter. Okay, so Jupiter will make up about 0.1%, and that's still not a lot, right? But then we have comets, which is, we'll talk about comets a little bit later, but they're like little ice, um, basically like ice that's flying through space. Again, we'll talk about that a little bit more in the future. Then we have all other planets and dwarf planets. So that would include all of our other planets. So Saturn, Uranus, Neptune, Mars, Earth, Venus, and Mercury combined. All of those combined would be about 0.04%. Remember, these are percentages. Okay. Then we have moons and rings, asteroids, and cosmic dust. Okay, so the main point here I want to make is that the sun makes up most of it. Jupiter takes up the next most, and then all of our other planets and dwarf planets make up a small, small amount. Okay. All right, so here is a bit of data on the different planets. I'm not going to go through everything, but just point out some main ideas here. So again, this is another depiction of our solar system, or the solar system. And these are the names of all the planets in order. closest to the sun. So we have the distance from the sun in AU, which remember that AU is astronomical, oh boy, I spelled that way wrong. Sometimes when I'm talking and I try to spell at the same time, it does not work well. Astronomical, there we go, unit, which is about 93 million miles, or about 150, no, 1.5, no, 150 million kilometers, I believe. Yeah, that looks right. Okay, and that is the distance from Earth to the sun. So notice that the Earth, that distance from the sun says 1 AU, 1 astronomical unit. So that is going to be that 93 million miles here, okay? So we have the distance from the sun. Then we have our revolution period. So revolution period is going to be the time it takes for the planet to revolve around the sun or orbit the sun. Okay, so orbital period, it can also be called. So orbital or revolution period. So I'm going to just go ahead and write that over here, revolution or orbit period, orbital period. Time it takes to orbit the sun. Okay, so again, if you notice, this is in years, and that's Earth years. So we say that for one orbit of Earth around the sun is equal to 1 year. Okay, and then again, all of the other ones are listed here. Then we have the diameter of the planet. So that would be, of course, the diameter, like a diameter of a circle, right? When we have a circle, we look at the diameter here. So that would be the diameter, and that is in kilometers. So we have those listed. Then we have the mass of the planet, and that's kind of like what we were just looking at, but we were looking at it in percentages of the overall solar system. But now this is going to tell us the exact number, the exact mass of the object, of the planet. So, for example, Earth, we have 59.8. And this isn't just in kilograms, this is in times 10 to the 23rd kilograms. Okay, so that would look something like, I'm going to say mass of the Earth is equal to 59.8 times 10 to the 23rd kilograms. Okay. So that's how we would write that. And we'll look a bit more at writing these large numbers, really understanding these large numbers this week. Okay. And then the next category is, or the next thing to measure is density. So density is going to be looking at the mass per volume. So density is mass per volume. So think of density as, I guess a good example would be like a pool noodle in a pool. Okay, so a pool usually has water. We can say it's just fresh water without chlorine, right? So it just is regular water to start out with. And then if you put a pool noodle in it, the pool noodle will float, right? And that's because this density. So the density of the water is more than the density of the pool noodle. Another good example would be air and water. So if you have like a water bottle and you have air and you have water in it because you've drank some, and you turn it upside down, the air is going to go to the top, right? And the water is going to go to the bottom. That's because they have different densities. So the density of water is going to be more than the density of air. So that's what we're talking about when we're talking about densities, okay? All right, so here is a big old list of looking at different types of planets, terrestrial versus giant planets. So, like I said, the terrestrial planets are primarily composed of rocks and metals, while the giant planets are composed primarily of hydrogen and helium, sort of like the sun. Okay, that's why a lot of times we call them gas giants as well. So sometimes, whoops, what the heck? Sometimes referred, whoops, doing great with spelling today, huh? Referred as gas giants. And this is why, okay? Um, The terrestrial planets are made of elements that are less common in the universe, so we get more abundance of rocks that are silicates or silicon and oxygen combined. And because of these other elements that are less commonly found, because they are heavier elements, if you've heard that term in a chemistry class before, we tend to get a denser planet. So these are more dense because of the elements that are making it up. Um, we also have that inside of the planet, so inside of the planet, we'll get some sort of differentiation because of density. So we'll have the lighter stuff on top, the light material on top, and then on the inside we'll have the denser material, or you can think of it as the heavier material, okay? So gravity is a huge proponent of this. That's why these things are happening, because gravity is pulling all of the elements in, all of the different types of material inside of the planet. Okay, so we've got um, typically a denser core, whoops, a denser core and a lighter as we go out. So we'll talk about this in the next slideshow, the next lecture, but talking about Earth, we have different layers, and this is again due to this differentiation of the densities. So again, denser material would be in the core, and lighter silicates that we see even on Earth, and I'll talk about that again, near this are near the surface to form some sort of crust, and that's where we get these um, rocky materials. Okay, so moving over to the giant planets. Again, they are mainly hydrogen and helium, and that's why they're usually called gas giants or gas planets. Um, but um, it is now known that they should be kind of almost like a liquid planet, almost, just because for example, Jupiter and Saturn are so large that the gas becomes compressed in the interior until hydrogen becomes a liquid. So it is under so much pressure that it's no longer a gas, but more of a liquid. Okay, and again, we'll have some sort of differentiation with the elements. The heavier stuff sinking into the middle, the lighter stuff would be on the outside, more of the gaseous um, material. Um, and some of the planets will then have like a rock or metal or ice core. Okay, and again, that's due to this pressure that it's under and the gravity that's pulling it in. Okay. Um, nearly all of the oxygen that's present in on any of these planets are combined with hydrogen to form water that will be in the form of ice. And again, that's due to this um, sinking of the heavier elements, and oxygen would be much heavier than a hydrogen or helium atom. Okay. All right, let's quickly talk about the origin of the solar system. So this is a quick depiction of this. Um, so about 4.5 million years ago, billion years ago, there was a dense cloud that started to form. And that cloud was made of interstellar gas and dust. And so that's what we see here in A. Okay. Now, eventually, this cloud collapsed due to some sort of shockwave or supernova, um, shockwave of a supernova, I'm sorry, that was nearby, and it formed a solar nebula, which is what we see here. So we've got um, almost like a disk. It looks like a disk that's around this sun-like item or sun-like volume, I guess you could say. And this disk eventually kind of like um, not dissipated, but different gravities kind of pull different chunks of material together. So um, that eventually would be here to see. So gravity pulled in um, a lot of material, including hydrogen atoms, combining to form helium atoms, and it released a lot of energy. And then this sun was born here in the middle. Now, there was a lot more material that was still circling the planet, or sorry, circling the star, the sun here. And so, as time went on, the matter kind of collapsed or combined with each other, clumped together and formed other objects that are in our solar system. So we've got asteroids, we have our terrestrial planets, and then on the very outskirts, we would have our gas giant planets or our giant planets. Okay, so this is the basic idea of what is thought to be the origin of the solar system. Um, and we will talk more about the sun in a future lecture. Okay, so for now, that's all we have for the just a brief overview of the solar system, and we'll get into the terrestrial planets next.